and welcome to CS350 Online. I'm your host, Leslie Eisted, and in today's episode we are going to we're not going to continue our discussion of processes or system calls because we're all done with that. We're actually going to start a new topic, which is virtual memory. But first, a few things. One of those is that assignment 2 is released and you can get started on that. Don't forget assignment 1 is due tomorrow or something. We will actually do an in-depth assignment 2 guide in episode 11, but that won't be happening next week because I've been informed next week is reading week. So sit back, have a rest. I know you all deserve a nice rest because everyone knows you probably work way too hard. So if you can take a nice break next week, do try to do that. There will be no episodes next week. They will continue at the following week. If you want to get a head start on A2, you can look at the previous terms episodes, and there are guides for A2A and A2B, and those are the 2 guides that you will need for assignment A2. So lots of things to keep in mind. We will do our best to keep on top of Piazza over next week, but keep in mind that office hours, and we might be a little bit slower to respond. Just keep that in mind. All right, now our OS of the day is one called PIC. Now, the PIC operating system was developed sometime around 1965, and it was released commercially in 1973. Company's TRW Inc., and the operating system was named after its creator, a gentleman by the name of Dick Pick. And what's really interesting about the PIC operating system was that it was actually Unix's biggest competition back in the 1980s, which is really surprising because you've probably never heard of the PIC operating system. So, what is it? Well, it's an operating system that has some different fundamentals in that it's actually based on a database. And so things like file retrieval and storing data were actually all done by a hash-based database system. And there was a query language built in as well as a procedural language so that you can actually build query-based programs. There was a compiled basic language as well, and it offered all of the things you would anticipate an operating system. So it had peripheral management, it supported multiple users with preemptive time sharing, and it used a modern implementation of virtual memory. But it was just based on a lot of a database transaction system, which is kind of neat. And we actually start to see more operating systems that operate in this way here on out. There's a few others. Now, obviously, this operating system wasn't really designed for everyday use. It's not meant to be something that your mom uses in her home. This is meant to be something that companies are going to use for their inventory applications. And it's because it's a database model. I mean, if you're just some 8-year-old kid who wants to play Space Invaders, you don't need a database operating system in order to play your game. So this was really meant for commercial inventory applications. And what's interesting is that you'll notice again, we haven't been mentioning what hardware this was developed for because this was actually ported to a lot of different hardware. And the other interesting thing is that this is actually still in use today, but it's no longer an operating system. What does that mean? So, what it means is that it's now just a database program that you can install on top of Windows. So instead of having the actual operating system be PIC, you're going to install Windows, and then you can install PIC on top of it. And you can do it that way. Now, who might still be using PIC? There's probably a lot of legacy companies out there. Companies have a tendency to not want to change how their world works. And there's good reasons for that. For one, how do you know that upgrading to a new database program or upgrading to the next version of Windows isn't going to break your existing system? And sure, your existing system may not be perfect, but you've used it for so long that you understand the ways in which it is flawed, and you know how to fix them efficiently and inexpensively. And if you move to something new, you've got to discover all of the new flaws and all of the new bugs, and it may not be as efficient or cost effective to fix those flaws or work around them. So a lot of companies will hang on to really old things. Like I know back in the late 90s, my mom was working part-time as a bank teller, and the bank wanted me to come in and look at their computer. And I was thinking, oh, it's going to be like a 486 or something. I'm going to go in and look at it. We'll see what's wrong with it. And I go in, and it's like a mainframe from the early 70s. And I was like, I don't even know what this is. And I mean, I tinkered around with the terminal for a little bit, but I couldn't figure out what was wrong with it because that predates me. But a lot of places are really reluctant to get rid of what they have because they understand how it works. So that's why, actually, if you're sitting there and you're like, I want to get a job that has really good security and will pay well, and I'll be one of the only people out there who can actually do this job. Well, I want to tell you, one of the things you can do to make yourself really marketable right now is make yourself a COBOL programmer. Because most of the people who are fluent in COBOL are actually retired or in the process of retiring. And so there's all of these companies out there that still use COBOL, and maybe they're trying to transition away from COBOL, or maybe they just want to keep it. And they don't have people to replace the retiring developers because nobody learns COBOL anymore. True story. I actually want to learn COBOL. It's not easy to learn, is my understanding. They tried to make it kind of English-like. And I've seen some other languages that are English-like Inform 7, and that is actually surprisingly hard to use, despite it trying to behave more like English. Anyways, an aside. So, PIC is still around. It's kind of cool. All right. So, I'm going to do a recap today. We're going to jump straight to our new topic. So, for those of you who are following along with the course notes, we are starting the virtual memory module. So, this is actually the biggest module of the course. And it's 57 slides. You can download it off the course website, of course. And to the Twitch user who says, oh boy, I can't imagine programming in English, I really recommend you look up Inform 7 because it's a cool programming language that's used for text-based interactive stories. And so it's I understand why it came to be, but it's actually really weird to use. I've tried to build a game in Inform 7 before, one of these text-based interactive stories, and it's actually quite hard to use. But I do recommend you look it up if you want to have some fun. All right, so virtual memory. That is our topic of the day. So, in the last 9 lectures, we've kind of glossed over what an address space is. We always say that a process has one and all the threads of a process are sharing it. We've briefly shown you what the contents of an address space are, but we haven't really talked about what an address space is, how you get an address space, how you know how big the address space is and what goes in it and where it goes. So we're going to be talking about a lot of these things over the course of virtual memory. Now, some of the time our discussion is going to be pretty high level, and then we'll also discuss some things like how does OS 161's virtual memory work. So, what I want to do to start with is I'm going to open up my notepad here, and hopefully it will actually open. And let's bring this over here. Now let's get us a new page. Okay. So, what is an address space? Let's first think about physical memory and what happens when we load a program. Load a camera. All right. So this is my RAM. All right. And it goes from address 0. We're going to use 32-bit addresses because we feel like it. Okay. Now, when I go to load a program, let's say I want to go and load... well, I was seriously thinking about how do you get Red Alert 2 to run on a Mac the other day. I've never actually seen it run on a Mac. I'm sure there's a Mac version out there. But how do you get that program to run? So let's say we're loading up Red Alert 2, which is one of my all-time favorite games. Or another game that probably would be easier to load is Unreal Tournament 1. Let's say you wanted to load up your favorite game. what actually happens? So when you double click on that icon, or when you type, the command at the command line, load, load star, comma 8, comma 1. Sorry, that's Commodore 64 command. But whatever your load command is, what actually happens in the operating system? Well, when you try to create a program, obviously it's going to create a process for your program to run in. And you create that process structure, and then it has to create an address space. When it creates an address space, it's trying to find how much memory do we need for the code, the data, including the heap, and the stack for this particular program. And so the operating system is going to go to memory and say, okay, I need this much memory for the address space. So it could say, okay, this is going to be your address space right here. And then what we'll do is we'll put, some code in there. And then we'll have our data. And then our stack. And this could go from, say, 0x that to, say, A. There's our address space for our program. Now, here's the thing. If this is the address space that I actually give to my program, then my program is using a range of addresses that directly corresponds to the physical addresses, the actual physical location where it lives in memory. But if you remember, what we actually want to do is we want to isolate processes, userland, from the actual hardware. So maybe we don't want to give the process these exact physical addresses. Maybe we want to hide them. Now, why wouldn't you want to actually abstract the address space addresses into something else? Well, here's one reason. Let's suppose I did use physical addresses for my address space. Then I know that the addresses for this program lie in this range here. And I could easily find that using some basic code I'll show you in a minute. And by virtue of knowing where in physical memory I live, I know where I don't live, which means I know that if I do 1,000, this number here, minus some bytes, I would be accessing memory potentially of another process that I probably shouldn't be. So by using direct addressing of the physical memory, then I can actually snoop around in the rest of memory and find other programs and find under their data, which means I can find kernel data, which means that I can get into things that I shouldn't be, and that's kind of bad. So we don't really want user programs to know where in physical memory they actually live. There's another reason why we don't want them to know. One of the big problems about the implementation of an address space we see right here is that we're allocating one contiguous chunk of memory to the address space. And if we do this, as we're going to discover very shortly, we will end up with physical memory becoming fragmented. That means that overall, there is enough space free. So all these blue regions here, if these blue regions were free, maybe that adds up to 3 gigabytes, and I need 3 gigabytes for my address space. But because those 3 gigabytes are not contiguous in memory, I can't actually allocate my new program because I don't have a contiguous region of memory for its address space to live. So there's 2 reasons why we are not going to use physical addresses for our implementation of an address space. One of them is a security and abstraction reason, because we don't want the user program to know where to go looking for other things. But number 2, If we use the physical addresses, then we kind of put the burden of having a contiguous address space in physical memory, which leads to a problem of external fragmentation. And we don't want that either. So what we're going to do is we are going to abstract these addresses. So I have a little program here I'd like to show you now. Excuse me. And what I'm going to do is I'm actually going to open a few more terminals here. And we're actually going to run the same program in each of these terminals. I know it's complaining at me. You're using ZSH. I don't want to use ZSH. I want to use bash because I am old-fashioned. So let's do clear bash. Apple likes to tell me, we don't want you using bash. We want you using this other thing. All right. So the program I want to show you is not that one. It is this program here. And I'll make this big just for now so you can see the program. So I have a global constant, I have a stack variable, and I have a heap variable. And then what I'm going to do is I'm going to print the address of main, which is this function here. So that's the address of my entry point function, which should give me the address of where my code lives. And then there's the stack, and then I'm going to print the address of the global variable, the heap variable, and the stack variable. And then we're going to wait for input, because that's what we're going to do. Now, question on Twitch is, even if you use virtual addresses, can't a program still go snooping around? Actually, it can't. And you're going to see very quickly why why snooping around doesn't work so easily. It's not to say that you can't. Certainly, hackers have exploited a lot of little flaws in implementations of virtual memory and, security in general to exploit that and do that. But generally speaking, no, you won't be able to just look, oh, if I go to my code address minus, I'll get somebody else's stuff. No, it's not going to work like that. And we'll show you why in a minute. So here's the program I'm going to run. And what I'm going to do is I'm going to run it 3 times, and they're all going to be running at the same time. So there's the first one. There's the second one. And there's the third one. Now, what's really interesting is let's take a closer look at the addresses that we see here. So what we see is main lives at this address here. Now, you'll note these addresses are really long. That's because I'm using a 64-bit system. So I'm actually using 48-bit addresses. We'll deal with that another time. So let's just look at the address of main is this. And then if I look down here, the next program, the address of main is here, and the address of main is here. And then it shows me where my global constant is. And then my heap variable. And then my stack variable. Now, these addresses don't exactly overlap, but if we had the belief that address spaces were a contiguous block of addresses from the start address to the finish address, then these 3 address spaces would technically overlap with each other. But they don't. It looks like they do, but they don't. Because these addresses that you see here aren't actually real. These are completely fake. So they're not overlapping. So let's close these off now. Don't want to make my computer any more mad than it already is. All right. So when we say these addresses are fake, we're saying these addresses are virtual. And what that means is that we're abstracting the actual physical address and replacing it with an address that is non-existent, like it's not a real address. And the reason why we do this is there's several reasons. One is to isolate processes from the actual physical memory. 2, to isolate processes from each other, because what's interesting is you're going to see that each process has their virtual address range is the same. So even though in physical memory they occupied physically different spaces, the virtual address range of every process is the same, which means you're effectively isolating the processes from each other. Because address 1000, if you're trying to read from it, you're going to end up reading from yourself. And you won't be able to go to a negative address to think that you're going to get somebody else's memory. Another reason why we're going to do this is because when we add the concept of virtual addresses, how we actually implement the memory, the physical memory, can be different. So if I don't want to use a contiguous allocation of physical memory, by abstracting the physical addresses into a virtual address range, I can actually be a lot more creative with how the memory is physically laid out, as we are going to see. And you did touch upon this, I think, in CS350, and you may or may not remember. I know CS350, I took that course in 1B, so I don't really remember much of it. No, it's a fun course. All right. So let's go back to our lovely slides here. All right. So physical memory. We are going to use some number of bits to address physical memory. Now, one of the things that I want to mention, and this always comes up every term, is there's a few people who get confused about what we are addressing. We do not address every single bit of memory. We're actually only going to address the bytes. So if we have a p-bit address, that gives us 2 to the power of p addressable bytes. So for example, in our simulated MIPS R3000, we use 32-bit physical addresses, which actually gives us a maximum physical memory size of 2 to the power of 32 bytes, which is equivalent to 4 gigabytes. And on things like your computer, so even though your computer is 64 bits, most machines are actually only using 48 to address RAM. So 48 bits gives you 256 terabytes. And I don't know about you, but I don't have 256 terabytes of RAM. If you have 256 terabytes of RAM, I'd like to know where you live so I can, come and see your computer. By that, I mean sneak it in the night and take it. I want that much RAM. That would be a lovely amount of RAM, 256 terabytes. All right, now in these slides, for the interests of fitting examples onto the slides, we're actually going to use our physical addresses as 18 bits, which gives us a maximum physical memory size of 256 kilobytes, which ironically is actually how much RAM my very first computer had, 256 kilobytes. All right. So, what's going to happen from here from here is that once we've got our physical addresses and we know how many bits we're going to use for the physical addresses, we're also going to need to figure out how many bits we use for the virtual address. I apologize, by the way, for the pause. It seems my network at home actually went down, so yeah, fun, right? Don't worry, though. You'll still get the content. So we have V bits set aside to use for our virtual addresses. Then that gives us a maximum size of virtual memory equal to 2 to the power of V bytes. So for MIPS, we use 32-bit virtual addresses, which again gives us 4 gigabytes maximum RAM size. Now, what's really interesting is that you don't actually need to have P and V equal to each other. So you can actually use fewer bits for the physical address or fewer bits for the virtual address. Now, how does that actually work? So if you are using fewer bits for the virtual address, that means processes are going to have smaller address spaces, which makes sense. And that will let, there's no issues there. And that's a very common thing. And in fact, in these slides, we're going to set the number of virtual bits to be 16, which means that we can actually only have an address space of 64 kilobytes in size. So that's pretty normal. So after that, I said you could also have the number of bits for virtual memory bigger than the number of bits for physical memory. And that's totally doable because the virtual addresses are abstracting how you've actually implemented the physical memory. So we can actually use huge virtual addresses and actually only use a tiny amount of physical memory. And we'll see better how that works when we talk about paging in great detail. Another interesting thing is that even though your computer, so actually having the number of virtual bits be different from the number of physical bits is actually a common thing. Maybe not so common now, but right around the time where we switched from 32 to 64 bits, this was actually pretty common. So you could actually, the ways that this happened is you could actually have a 64-bit architecture. And so your RAM, you could have a lot more RAM than your 32-bit program could actually access. So the virtual bits might actually be significantly smaller, preventing you from actually accessing a lot of your physical memory. So that was kind of cool. And actually, it's one of those things where if you're actually writing a program where you need a lot of memory, make sure you're using 64-bit, because I know in my own programs where I wasn't thinking about this and I was compiling as 32-bit, I ran out of memory way before I was done using memory. So make sure if you're using a lot of memory that you do compile as a 64-bit or target a 64-bit, because otherwise you'll only have an address space size of 4 gigabytes. And if you've got, in my case, I had a 4 gigabyte image I needed to load into the heap, yeah, that's not going to work. So pay attention to that. Now, what gets a virtual address? So is it going to be just the actual heap data? No, actually it's everything. So every part of a process is going to run as a virtual address. So that means the program counter, the stack pointer, so every instruction address, every branch target, every address of every variable, everything is going to be a virtual address. Which actually raises an interesting problem. If you've got all of these, if every address associated with your process is a fake address, then what ends up happening is, how does the CPU actually know what to do with these? So we're actually going to need some mechanism by which the CPU or the kernel of the operating system can translate from the fake addresses to the real addresses so we can actually find the code in the actual physical memory. We'll deal with that in a couple minutes. But here's just a rough idea of what's going to happen. So this is our example. Please ignore the 28 kilobyte used here. It's a typo, and I don't have Illustrator anymore to fix this. So what you see here is we've got our 18-bit physical address. So there's 256 kilobytes of available memory. And our virtual memories, they can have a maximum size of 64 kilobytes because we are using 16-bit addresses. But that doesn't mean we use all of virtual memory. So the size of the address space is not equal to the size of virtual memory. The address space might be significantly smaller. It's just how much virtual memory we're actually using. So process A may actually only use 28 kilobyte of the available 64. And process B, likewise, may only use 48 kilobyte of the available 64. Now, we already talked about why we do this, so we'll skip this. So I said address translation is going to be a problem because if every single address is a fake address, then how could the CPU ever know, like, address 0? Oh, but that's not a program instruction. That's null, or it wouldn't know how to interpret those addresses. So every single virtual memory address, before it's executed, actually has to be translated to a real physical address. And the question becomes, how do you perform this translation and who performs this translation? So you might be thinking, okay, well, let's have the kernel perform the translation. The kernel implements virtual memory. It's going to perform the mapping between physical to, create the mapping from physical to virtual. So it makes sense for the kernel to do the translations. But that would mean, per assembly instruction, we have a minimum of 1, possibly 2 exceptions raised just to do to address translations. That's going to be so horrifyingly slow. So we don't want the kernel to be doing the majority of the translations. What we want is for the hardware to be able to do the translations itself. So we actually have a piece of hardware on board that's responsible for doing those hardware translations, and it's called the MMU, or Memory Management Unit. And what's going to happen is for every address, we're going to pass it through the MMU, and the MMU is going to know how to translate that address for that process to its actual physical address, which means that the MMU will actually be interacting with on every context switch, because we'll need to update some information on the MMU to let it know, hey, here's the new translation information for the new process that you're running a thread from. So what we're going to do is we're going to spend the next day or so talking about some of the different address translation schemes and their advantages and disadvantages. Now, just a little bit of history here. So I'm going to go back. There's a little history bubble here. This concept of virtual memory is actually really, really old. It goes back to 1956. And some of the very first commercial operating systems to actually implement virtual memory were the Burroughs system, MCP, in 1961, and the Atlas in Atlas in 1962. So this is an old idea. And what's really interesting is that the earliest versions of things like Windows and DOS and macOS actually didn't use it. Yep, that's a fun story. We'll talk more about that later. So our first address translation scheme is the simplest, and it's called dynamic relocation. And the idea is you have a contiguous block of virtual addresses that make up your address space in virtual memory, and we are going to find some contiguous equal-sized block of physical memory in which to map that contiguous block to. So this lighter purple here is going to be the mapping for process A's address space, and this yellow is process B's address space mapping. And what you see here is that process A actually lives at address 24,000, but that start address is going to be mapped to 0. So we're going to subtract what's known as the offset to go from the physical address to the virtual address, which means to go the other direction from virtual to physical, we're just going to need to add the offset back to the virtual address, and that will give us our actual physical location. And we also keep track of a limit so that we know how big the address space actually is. And so the MMU then has just 2 registers of information. The first register is called the relocation or offset register, and it says where is the starting position in physical memory for this process's address space. And then the second register, L, is the limit register, because I don't want to try to translate addresses that are outside of this address space, because that would be very bad. I would be translating stuff that's garbage, or I would start allowing the reading and writing of memory that isn't mine. So we have a limit. And the idea behind the translation is, given some virtual address V, if V is less than the limit, then the physical address it's a valid address in the address space. So the physical address is just the virtual address plus the relocation register. If, however, the virtual address is greater than or equal to the limit, then we throw an exception. And it's really important on any tests that if you can't translate the address, you say exception. All right. So why is it the virtual address equal to the limit gives us an exception? Because memory is 0. We count starting at 0. So an array that holds 10 elements has indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not 1 through 10. Hence why it's less than L is valid, and greater than or equal to L is not valid. So this is dynamic relocation. Really, really simple. Now, when we are doing these address translations, there are 3 primary goals that we actually have, and we should talk about them. The first goal is transparency. I need to make sure that the process or program is not aware of the fact that the addresses that it's using are real. It should never be aware of that. Because if it's aware that the addresses are fake, then it would know something about reality. We don't want it to know about reality. Okay. The second important goal that we have for implementing things is efficiency. So the act of translating the addresses should be efficient in terms of execution time and space. So some of these translation mechanisms are going to require the storage of additional information, and we need to make sure that it doesn't actually need a lot of extra information. So we want to keep the amount of time used to perform the translations down, but we also want to keep the amount of space down. And the final goal is protection. So it actually has to provide the isolation from the physical hardware and from other processes. So does dynamic relocation meet these 3 goals? It does offer transparency because the process wouldn't be aware that the addresses were fake. It does offer protection. And it is very efficient. And it's very efficient because per process, we only need 2 integers stored. And then the address translation itself is a very simple add. Can't get any more efficient than that. So you might be asking, so is this the address translation scheme we use today? And the answer is no, because this method actually has a huge flaw. Massive flaw. And the massive flaw that dynamic relocation have is this concept of fragmentation. So I showed it to you before on OneNote. But the idea behind fragmentation is if you're doing a bunch of allocations of a specific size, so there's some allocated memory. That memory is allocated, and this memory is allocated. For dynamic relocation, we require contiguous allocations. So I can't split an address space between A and B here. They actually have to be together. But the problem is, even if A plus B is the right size, since they're not together, I can't actually create the process. Now you might be like, well, what if we shifted things around? Well, how long does that take to shift things around in memory? You don't want to have to defrag your RAM while you're trying to load a program. It's not to say that there's no OS that hasn't tried to do this. It's just this is kind of inefficient. So dynamic relocation is a very, very simple and efficient scheme, but it also suffers really badly from this external fragmentation, which causes us to not want to use it. The other problem is that if you actually look at how an address space is laid out, helps if I have the right sides open. So if you look at how an address space is laid out here, address spaces aren't laid out as code, data, stack, like all together, tightly compact. They're actually spread out to give things like the heap and the stack space to grow. This is actually a picture of the address space from OS 161's sort program. And in purple, that's where you'll see the where the code segment lives, and the yellow is where data lives, and then the stack is this magenta that's in the middle. And the problem is, because the address space would be contiguous, every address space in OS 161 would actually be 2 gigabytes in size because we can't break it up into smaller parts. Which means that if we use all address spaces are 2 gigabytes, we don't get external fragmentation. We get internal fragmentation where we've got large chunks of allocated memory that we can actually never use. So dynamic relocation has a lot of restricted behavior. It's also going to limit how many processes you can actually run because it's going to limit how many can actually fit into physical memory. Now let's play around with some address translations. So I'm going to open OneNote back up. We're going to do the address translations for couple of these, and then I'll let you do the other ones on your own. So let's get a new page. Put some lines down. So for process A, we have a limit register of 7,000 and a relocation register of 24,000. So virtual address 1 is 0x102C. So the first thing we do is, being the human MMU, we are going to compare our virtual address to the limit. And we see that 102C is actually obviously less than 7,000. So I'm just going to add this to my relocation value, which is, so my physical address for the first one in process 1, 2502C. Now for the second one, we have virtual address 8,000. Now this is interesting because when I compare this to my limit, I see it's bigger than my limit, which means I can't do a translation, which means I get an exception. That's fun, right? And then the final address is 0. You'll note here that I've truncated the address just because all those extra zeros aren't actually needed. Be careful because we do that a lot. And that's obviously less than the limit, so the physical address here just ends up being 24,000. Now, as proof that virtualization isolates processes from each other by isolating their address spaces, I will do one address for process B, and you can do the other two. So let's do virtual address process V, same virtual address as process A. So 102C, but you'll notice that our limit and relocation now are different. The limit is C1000 and the relocation is 13,000. So obviously 102C is less than C1000, so my physical address becomes 14,002C. So what does that mean? These are the same virtual addresses, see? Same virtual address. But due to the fact that their translation scheme is different, you can actually see that they map to two different locations in physical memory. So virtual memory plays a huge role in isolating processes from each other. And to make this work, you need to obviously make sure that when you do a context switch between threads of different processes, you are going to have to update the MMU to say, hey, MMU, this is your new relocation and limit value for your new process. Okay. Very simple. Not quite what we're looking for. So, can we do better? I mean, you know the answer is yes. So one of the observations we make about this is the fact that in the address space, there are actually large sections that are empty, and that the layout is not contiguous. So if we wanted to stop wasting all this internal space, maybe what we should keep track of is just the segments of the address space where we actually store data, because there are a limited number of them. And if we do that, then I would have no internal fragmentation. And this is actually the idea behind segments. So the idea is we're only going to keep track of the regions of the address space we're actually using. So the code segment, the data segment, and the stack segment in the case of OS 161. All right. But if we're going to do that, then we're going to need to kind of have a mapping for each of the segments. So I need to know each segment is going to be contiguous in physical memory, but I'm only going to keep track of the individual segments. And where they live in physical memory, they can be scattered to the wind. It doesn't matter, but the segments themselves will actually be a contiguous allocation. So I need to first figure out, how do I identify which segment this virtual address belongs to? And what we're going to do is we create a two-part virtual address. That was fun. That's a fun bug. So our virtual addresses are going to look like this. The highest order bits are the segment number, and then the remaining bits are what's known as the segment offset, or the address within the segment. How many bits do you need for a segment offset? Well, it depends on how many segments you need. So the number of bits for the segment number is the log, and this is base 2, of course, of the number of segments. And, of course, you're going to need to take the ceiling of that because we can't have a fractional number of bits. So if I have one segment, I need 0 bits for the segment number because there's only one segment. If I have 2 segments, I need 1 bit for the segment number. 3 segments, I need 2 bits. And so on and so forth. So how my address translation works then is that we are going to have to first figure out what the segment number is. Once we figure out the segment number, then we can use the segment number to look up the correct relocation and limit values for that particular segment, and then we can perform our address translation. Now, having a 2-part address puts some restrictions. So for one, if there are 2 to the power of k segments, we are actually restricting how big each of those segments can be. So the maximum size of any segments is 2 to the power of v minus k. So for example, if I have 16-bit virtual addresses and I have 2 segments, then the maximum size of any segment is 2 to the power of 16 minus 1, which means it's 2 to the power of 15, or 32 kilobytes is the largest segment size I'm allowed to have. But I can have 2 segments at that size. Now, this is going to solve our internal fragmentation issue, but one of the things it's not going to solve is the external fragmentation issue. So this does improve things, but we're still left with an external fragmentation issue. Why are we left with an external fragmentation issue? Well, actually, it's because each allocation of physical memory is a different size. If all the allocations are the same size, then you don't have to worry about external fragmentation. But our allocations are all different sizes, so we still have external fragmentation. Though that being said, this address translation scheme is actually quite popular, and I believe it was the first one that Microsoft Windows actually used. And it worked, of course, because you couldn't actually run many programs at the same time in the early days of Windows, so the external fragmentation issue never really became a problem. Your computer probably crashed before it did. So let's take a look at how this actually works. So here we have our 2 address spaces. We're going to do 2 segments per address space. So we've got segment 0 and segment 1. And then what happens is we can map segment 0 anywhere in physical memory and map segment 1 anywhere in physical memory. Same with this 0 and 1 for process B. And then for each segment, we keep track of the offset and limit so that we can actually perform the translation once we figure out which segment things belong to. The address translation, however, there are different ways that this can be implemented. We are going to talk about 2 different ways to implement segmentation, but it is by no means all of the possibilities. So the first approach is that the MMU just has registers for the relocation and limit for each segment that's possible. So your architecture is dictating how many segments you are allowed to have. You are only allowed to have 2 segments. And if the MMU only supports 2 segments, then the MMU will have 2 relocation registers and 2 limit registers, one of them for each segment. So if that's our implementation, then the first thing we do is we're going to separate the address into the segment number and the segment offset or address within the segment. If the segment number is invalid, then we throw an exception straight away because it's not a valid segment number. And that can happen, by the way. But if it is a valid segment number, then we're going to take the offset and we're going to ask, is the offset less than the limit for this segment. And if the offset in the segment is less than the limit, then it's a valid address, and we're going to add the relocation value for that register, for that segment, to that segment offset, and that will give us our physical address. If, however, the address within the segment is equal to or greater than the limit for that segment, then we throw an exception because we know it's outside. And, true story, you want to know where the term segmentation fault actually came from? It actually came from this implementation of virtual memory, where a segmentation fault meant that you're trying to access memory outside of one of your segments. So this does not belong to the segment. Kind of fun story anyways. Term kind of stuck, even though we don't really use segmentation anymore. All right. So, what is the second approach? So, and again, there's more than the two approaches. There's always more than two ways to do something. So, the problem with the first approach is that your MMU is going to get really, really big, and it's truly dictating how many segments the hardware should be using, or the software should be using. I don't know about you, but I don't like being told what to do. So, I don't want my hardware saying you must use 2 segments. I want some flexibility. Now, I understand my hardware is going to impose some limitations on the maximum number of segments I want to use, but I don't want it to dictate exactly how many I have to use. The other thing is that the more segments you need, the larger your MMU is actually going to be, because you'll need more space for the registers on the physical chip. And that takes up space, and space comes at a cost on a chip. You don't want to be wasting space with registers on a CPU. So, the second approach has a much simpler MMU. The MMU has only 2 things. That is a segment table base register that essentially says, here is a pointer to RAM where you can find a table that contains the mapping between the relocation value and the limit for each segment. And a second register that stores how many segments you're actually using for this process. So the MMU is much simpler, but now our translations are all going to be going through memory because we'll have to look up the information for that particular segment in RAM. So how this address translation works is pretty much the same. If the segment number is not valid, then we throw an exception. Otherwise, we're going to use the segment number to look up an entry in the table, which is in RAM, and then that table entry will have a relocation and limit value, which we will immediately use to perform the translation and either throw an exception or actually get the physical address. Now, what's really nice about the table approach is, let's suppose you wanted to support things like a read-only segment, i.e. your code segment should be read-only. The table method lets you easily have things like protection bits to indicate, hey, this segment is read-only, or hey, this segment hasn't been used recently. Whereas if you wanted to support that in the other implementation, you'd need even more registers built in. So in a lot of ways, this segment table approach is much more flexible. Now, let's do a little bit of translation here. Now, I'm only going to do process A, and I'm going to let you do process B on your own for practice, you know. Okay, so let's start. We see we have 2 segments. If I have 2 segments, I know I'm using 1 bit for the segment number, and it's the highest order bit. So actually, I think I want, helps if I'm on the right page. So I'm going to create a table here. So there's my virtual address. And there's my virtual address. Now let's look at my segment number. My segment number is the highest order bit, not the highest order hex digit. So what you have to remember is that each hex digit is actually 4 bits of information. So this 1240 is actually that address in binary. And so I'm looking at my highest order bit here, and I see it's a 0, which means that this address is in segment 0. And if I were to look at the bits for A0, I would see it's and so I know that my segment number, not 10, but is actually segment 1. Similarly, 66AC, that's going to be in segment 0, and E880, that's going to be in segment 1. Okay, now I need to know my segment offset. To get the offset, we are actually going to set the segment bits to 0. So whatever the segment bit is, set it to 0, and then the new address that you get is the offset. So in the case of 1240, since the segment bit was already 0, we just get the offset is the same. Same for 66AC. Now for A0, what I'm going to end up getting is I need to set this highest order bit 1 to a 0. So I end up now with that being my highest order number. And so this one is now 20A0. So that's my offset for address 2. And then for E, which is that, I'm going to end up instead with 6880. Okay? So now we can do our actual translations. I'll do them in a different color here since I'm running out of space. So I check the limit on address 1. It's within the limit, so I can add it to my address. So I end up with my physical address for this one is 39240. And then for the second one, I look it up and I see, is that within the limit? Yes, it's within the limits. So I'm going to get an address of 120A0. The third address, I look that up and I see that 66AC is bigger than the limit, so I get exception. And then I'll put the one for this one down below. 6680, that is bigger, so we end up with an exception here as well. And I'll let you try the same for process B. The way that we actually perform the translation is the same regardless of our MMU's implementation. So the math is the same. It's just how is the MMU implemented. All right, so that's segmentation in a nutshell. We solved some of our problems, but not all of them. And the problem we didn't solve is the external fragmentation problem. But otherwise, this scheme is really good. It's really efficient. It offers transparency and it offers protections. It's a very good scheme. It just has a little fragmentation problem, which admittedly is a much bigger problem today than it was back when this was commonly used. Okay. Can we do better still? And the answer is yes. Obviously, we can do better still. Because what we can do is we can try to get rid of this idea of having our allocations be different sizes. We can get rid of external fragmentation. And how we do this is through paging. Now, I'm going to briefly introduce the idea today. I don't want to go too in-depth. I'd like to come back to this in a lot greater detail after reading week because we're going to do a lot of math with this. But here's the idea. If you want there to be no external fragmentation, then you need to guarantee that every single allocation is the exact same size. So what we're going to do is logically, that means in code, subdivide physical memory into equal-sized chunks known as physical pages or frames. Now, just for the sake of our slides, but also for if you look at the computer sitting in front of you, the most common page size here is 4 kilobytes. The next thing that we're going to do is we're going to logically subdivide virtual memory into equally sized pages. And the page size for virtual memory is equal to the frame size for physical memory. So these, for our example, are also going to be 4 kilobytes. So everything is now divided up into these 4 kilobyte chunks, and you can't have half of a page. If you have any data on the page, you have the whole page. So there's a small amount of internal fragmentation, but let me ask you this. If you've got 64 gigs of RAM and 1,000 processes, do you care if 1,000 processes each weighs 3 kilobytes? That's only 3 megs out of your 64. So we don't really care because the amount of internal wasted space is really, really small. It's almost negligible compared to the size of our RAM. But what's really cool is we're not going to have any external fragmentation. What we're going to do is instead of allocating, these 7 contiguous pages of virtual memory in physical memory, we say, okay, just give me any 7 pages of physical memory. And I will map each page of virtual memory to some random page of physical memory, and that'll be where I live. That way we don't have any fragmentation because each allocation is exactly the same size. However, there is a huge downside to doing it this way. And the huge downside to doing it this way is now, instead of having to keep track of, just a few relocation limits, we don't need to keep track of limit because the limit's 4 kilobyte because every page is the same size. But we do have to keep track of the relocation value for every single page. And you might be thinking, that's not a big deal. Really? I mean, for us, in our little example, it's not a big deal because our page tables, which keep track of the mapping from page number to frame number, only have 16 entries. But, just to give you a little look ahead, what I want to tell you is that as the size of your virtual memory increases, so too does the size of your page table. Because the size of the page table is equal to the number of pages of virtual memory that you have, not the number you are using, the total number of virtual memory pages there are, multiplied by the size of each entry in the table. So if we use a 48-bit virtual address, that actually means that our page table size is 2 to the power of 38 bytes, or 256 gigabytes. Remember, we needed to be efficient in terms of how much space we're using? That's not very efficient in terms of space, because 48-bit addresses, what we're using right now, needing a 256 gigabyte page table to translate hello world? That's insane. That doesn't make any sense whatsoever. So there's a downside, and we are going to fix it. And we'll talk also about how our translations are going to work in our next episode. Cliffhangers. We like cliffhangers. And it looks like we're live again. So for anyone who's actually still hanging around, don't worry. The whole episode will be up on YouTube as soon as I get it uploaded. So you haven't missed anything. You've just missed some of the live experience. All right, so next episode, which is number 11, will happen after reading week, and that will be how to do A2. And then we will come back to talking about paging in episode 12. So lots of time. So we will see you after reading week. I hope you have a great week. Have some fun. But maybe don't travel so much. That's probably not a good idea.